To explore quantum networks, we will start by working through a detailed example of a quantum network. In this example, we have two parties, Alice and Bob, who need to communicate top secret information. There are many types of information that need to remain secure, such as information related to defense and military, intellectual property, financial information, medical information, etc. Keeping information secure can be a matter of personal, organizational, and even national security. Alice and Bob have decided to use an entanglement-based quantum network to communicate their top secret information, as it is the only provably secure option. They will use entanglement-based key generation via the BBM92 protocol to secure their communications. It's important to note that there are many other entanglement-based applications beyond key generation that can be used to help secure communications. The family of all such applications are known as Quantum Secure Communications, or QSC. Alice and Bob are located 200 kilometers apart. This means that they cannot use a single point-to-point connection for their quantum channel, as point-to-point connections typically only support links of up to 50 to 100 kilometers. However, through the use of 3 intermediary nodes in the form of quantum repeaters, evenly spaced between them, Alice and Bob will be able to utilize their quantum network and secure their communications. In our graphics, we will use a blue line to represent Alice and Bob's quantum channel, and a red line to represent Alice and Bob's classical channel. We'll give a list of the hardware components employed by Alice and Bob's quantum network. Each of the 5 nodes contains entangled photon sources to produce entanglement on each individual node, quantum memories to store quantum information on the nodes, CNOT gates for an entanglement purification protocol, which we'll discuss later, Bell state measurement stations, and in this case we'll be using probabilistic Bell state measurement stations, which are made up of single photon detectors and beam splitters. We'll be using these Bell state measurement stations for our elementary entanglement generation protocol and entanglement swapping protocol, which again we'll discuss later. Alice and Bob's nodes will use quantum random number generators to provide true randomness for BBM92. Classical communication will be used in our quantum network protocols for things like heralding results, timing and synchronization, etc. It's important to note that quantum networks will not be used to completely replace classical networks, but instead will be used together with classical networks to enable performance in new applications that neither network can accomplish on its own. There are 2 important things to note about quantum network hardware. First, while repeaters, the intermediary nodes used to extend the distance of distributed entanglement, are not commercially available, the components that they consist of are. Second, hardware used by quantum networks can differ in types of components used and makes models and vendors of the components. Components will continue to evolve and requirements for each network will differ, so there might never be a uniform set of components used for all quantum networks.